Hello. Look who woke up early today. Alright. Hello, my name is Mr. Shu. It's your turn. Say, hello, my name is Hannah. Okay. Say, I love you. Bokiga. Yeah. Wave. Say, hi. Alright, say bye-bye. Okay, so my daughter is awake now, so if you hear her in the background, I apologize beforehand. But, I am recording this in my house. So let's continue. I'm obviously, again, not in class, but let's continue with sampling distributions. And so today, real quick, I should probably go back to the beginning. Today we're going to finish this section. So in other words, what we're going to be talking about is we're going to be talking about how to determine whether a statistic is an unbiased estimator of the population parameter. So in other words, this fourth objective. And then how to describe the relationship between the sample size and the variability of an estimator. Now, hopefully by the end of this video, you'll have a good understanding for what those two phrases mean. So we're going to talk about how we know essentially when a statistic is a good estimator for the population parameter, and how sample size plays into how variable of an estimator we have. So like if our sample size is larger or smaller, what difference does it have? And you probably already have an idea of this from chapter 4. But we'll talk about it in a little bit more detail soon. Okay, so yep, hopefully this will be good. Okay, so let's continue. So what we're going to talk about today is essentially how can we tell whether our sample, the first thing we're going to talk about is how can we tell our sample is a biased or unbiased estimator. And the way to do that is, by definition, is that it's an unbiased estimator. Like the way that we know our statistic is an unbiased estimator is through the sampling distribution. So a statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution is equal to the true value of the parameter being estimated. So in other words, what we concluded with the other day is actually the definition of an unbiased estimator. Like if I have a sampling distribution here of some distribution of P, in this case, if we talk about the cards again, or the chips in the barrel. In our case, it was cards, but we were taking sample sizes of 20 from a proportion of where half of the cards were red and half of them were black. In this case, it's red chips versus blue chips, right? But both proportions are 5. So let's assume that this is the sampling distribution for the cards within my population. And so because the mean of this is 0.5, the p hat, the mean of all the possible samples of p hats is actually 0.5, which is the actual value of the population p, then the way that I've collected my sample is unbiased, because the mean of all the possibilities is actually the value of the population. That is a definition of an unbiased estimator. So, please don't say things, please don't use definitions like, if I don't do voluntary response, or I don't, if there's no non-response involved, or if there's no undercoverage involved, like, these are all true statements. Like, if you don't have undercoverage, if you don't have non-response, if you don't have voluntary response, if you didn't sample convenience using a convenience sample, these all contribute to your estimator being an unbiased estimator. However, that's not the definition, right? So, like, if I ask you, like, why is my sample mean or sample proportion an unbiased estimator, literally the definition is, well, the mean or of my sampling distribution, or whatever it is, whether it's standard deviation or other estimators, right? But let's just say mean. Like, the mean of my sampling distribution is the actual mean of my population, and because that is true, then my estimator is an unbiased estimator. That's the definition. Yeah. So don't say things like, oh, well, there wasn't undercoverage. Like, these don't really help. Okay, like, these are all true, but the definition is essentially the way that we know it's unbiased is if this mean of my sampling distribution is exactly what the population proportion is. Now, that is the theory. In real life, is it possible to eliminate bias? And the answer to that is no, right? Like, we've talked about this, right? So there's always going to be a little bit of bias, right? So yeah, but this is, like, theoretically, in a perfect world, if the mean of my sampling distribution is exactly equal to the population, then my estimator, whatever it is, whether it's X bar, whether it's P hat estimating for P, or X bar estimating for mu, these are going to be unbiased estimators. Okay? All right. So, let's continue. Okay. So, we're going to talk about variability now. The last thing we talked about was bias. Now we're going to talk about variability. In other words, with bias, this ensures that you don't really overestimate or underestimate your values, which is really important. But just because you have an unbiased estimator doesn't mean that your statistic or your statistic will be close to the actual parameter value. Another very important aspect of when you gather your sample is the variability. Okay, and so essentially with variability, like we learned about this a little bit in the last section, right? Or not the last section, in chapter 4, where we were looking at the principles of experimental design, and we talked about replication, right? And replication is that the larger your sample, the better, essentially. It's going to be more representative of the population. And if you think about that, it makes sense, right? If I took a sample of 4 cards from a deck of cards, the likelihood that I get, like a sample that is close to the mean, exactly 2 red and 2 black, versus 3 red and 1 black, or 4 red and no blacks, right? Like the proportion value of red to black is going to have very high variability in that case. Whereas if I took a sample of 20 or a sample of like 100, obviously the deck has to be huge, right? The variability is going to be a lot less. So here, essentially, what this slide is saying is that the larger your sample, the less variability it's going to have. Like, if you take a look at this, I'm not sure what this is a sampling distribution of, right? But it's a sampling distribution for something, if it's an unbiased estimator, that has a mean or a proportion of 0.37. And the mean of both sampling distributions is 0.37, except this one, the sample size is 100, and this one, the sample size is 1,000. Now, the sample size of 1,000 has a lower variability, which means you have a higher chance of being close to the mean, or to close to the actual proportion, sorry. Whereas here, there's more variability involved. In other words, if you were to collect a sample, right, there is a higher chance that even though it's an unbiased estimator, that your sample is not going to be very close to the actual proportion of the population, right? So the two main aspects, like other than, you know, like making sure that your sampling method was unbiased, is, you know, if you gather a larger sample, then you have a better chance. Now, again, there is no guarantee ever that you are going to be able to get a sample that is going to be exactly what the population. It doesn't matter whether you have low variability and you have an unbiased estimator. There's no guarantee that your sample is going to represent the population exactly. So my question to you right now is actually this. Which one do you think is more important? Variability or bias? Okay, think about it for a little bit. Okay? Now, if you guessed that bias is more important, you are correct. Okay? You are correct. So, bias is much more important, and this is an illustration of that, right? If you have this like diagram right here, if like let's say this is a target, right? And this is the true population, proportion, mean, standard deviation, whatever it is, median, Q3, Q1, could be anything, right? And you have high bias and low variability. This is actually pretty bad, because if you're high bias and low variability, you're actually going to be very, very, very far off the actual population parameter. Okay? Now, if you have low bias and high variability, there's still a chance that you're going to be on the mark, right? And then obviously if you have if both are bad, right, then that's probably the worst, because you just have no idea in general, right? And then the ideal is no bias and low variability. Okay? All right. Very good. So what I'd like for you to do at this point is to look at this problem right here and take a couple of minutes, or actually you'll take let's give you 15, or not 15, let's give you 7 minutes to solve this real quickly. Okay, cool. Okay, see you in a bit.